Hello everyone, and welcome to this video short where we are going to go through an example using Network X to solve a min-cost max flow problem. And so here we're going to investigate this via a really simple example just to introduce the syntax and identify how to execute the solver in Network X. As we've seen previously in this class, the use of networks in general and reductions of existing problems into graph-based problems can be a really powerful tool for modeling data and solving data science problems. The key here to doing this reduction, or key to using a graph-based model to analyze data, is to design the graph correctly. And by design the graph correctly, I mean we need to define the nodes, define the edges, and then make connections between the nodes and edges to model our data science problem appropriately, and then assign attributes to the edges appropriately as well, again, to model the problem at hand. So if we have a flow problem, we need to identify what the capacities are, and then also conceptually, what do they represent? If it's a road network, are the capacities sort of the maximum amount of travel that can pass through that road per unit time, right? If it's a social network, is this the number of messages that can be passed, maximally speaking, from one person to another on the social network, etc. And also, we need to consider what other types of attributes might we assign to the edges on the graph. Are there any other weights, penalties, costs that we want to analyze or keep track of? In this scenario, we are modeling a simple version of something like the transportation problem, where we want to identify a maximum flow of goods through some transportation network at a minimum cost. So there might be multiple ways to get the goods from suppliers to consumers or demanders, but we want to find the way that's going to give us the most efficient solution, or the minimum cost total. And so setting up this graph is key. And in this particular example, we just have two nodes that represent suppliers and two nodes that represent consumers. And we have the total amount of goods that can be received or that are requested by each of the consumers. And we know the cost to transport from each supplier to consumer, which is going to be a little bit different for each one. And given this information, we can set up our graph and then transform this, essentially reduce this to a max flow problem where we want to find the min cost of the max flows. All right, so in this particular example, we're going to say that node number 2 has 50 units of goods and node number 3 has 50 units of goods, and that the consumers, node 3 and node 4, have requested 40 units and 60 units respectively. Right, now the cost incurred, either because of geographic location or some other logistical issues, for transporting the goods is going to be different from node to node, from supplier to consumer. So here we'll say that there's no penalty. So the penalty from getting the goods from node 2 to node 4 will be 0, and the penalty or the cost from node 3 to node 5 will be 0. However, we'll incur a penalty of 1 if we transport from 2 to 5 or from 3 to 4. All right. So let's go ahead and set up this network. Looking at our code here, again, we need to simply import network X. And if we want to visualize this, we can also import matplotlib. Then to set up the network appropriately, here we have all of our our edge list. And again, to turn this into a max flow problem, we want to add a source and we want to add a sink. And so I've added a source node, being node number 1, and a sink node, node number 7. So to set up our suppliers, I attach as you can see here, the source to each of the suppliers, and each of the consumers are attached to the sink. Again, to sort of set up our bipartite graph, and we've separated into the suppliers and consumers, and we want to add our source and our sink to each, so we can get this turned into a flow network. And then the interconnectings of our bipartite graph here represent the ability of a supplier to supply goods to a consumer, and then the penalty associated with each. So here, again, the capacity simply represents the amount of goods that that particular consumer has requested, and then the associated penalty for transporting from that supplier to that consumer. All right. Now, if we want to visually confirm the structure of our graph, we can do so using the draw function from NetworkX, which is done here. If we want to get a bipartite layout, which is a great way to visualize a network like this, we can use the bipartite layout function, again associated with NetworkX. In order to do that, you need to identify the sort of the first set in the bipartite graph so that it's separated out. Again, here, it's not perfect because we have our source in here. So the source, of course, you might want to be drawn slightly off of this axis because it's not a supplier. However, given the limitations of NetworkX, this is a simple way to illustrate this rather than going overboard. Right, and so here we have our source connected to our two suppliers. Note that 2 and 3 are not connected. This is the extra arrow connecting 1 to 3 here. Similarly, we have our consumers over here. And note that 4 is not connected to 5, but rather 4 is connected to 7 and 5 is connected to 7 rsync. And then here we are fully connected in our bipartite graph, as any supplier can supply goods to any consumer. However, the penalty for each is different, as we noted here in the edge list when constructing the graph. All right, now if we want to analyze the flows or the max flows or the min costs or the costs of different flows, we can do so using our built-in tools in NetworkX. So again, this is great because we've reduced this now to a flow problem. So all of our algorithmic solutions, our tools that exist for analyzing flow, for calculating min costs, for max flows, we can now assign to this transportation problem. And so here, we can just simply get the max flow or the min cost of the max flow, calling that function in NetworkX. We can get the cost of any flow by calling that function in NetworkX. All right. And so here, if we were to print this out, we can see that the flow for the min cost here is as follows, right? From our source, we get a flow of 50 to each of the suppliers, right? Of course, to get the network started. And then from supplier node 2, we can get a flow of 40 to node 4 and a supply of 10 to node 5. And for node 3, we can send a supply of 50 to node 5. This is intuitive because this particular flow, again, is maximizing the amount of transportation that's going to give us 0 penalty or 0 cost, and thus giving us a minimum total cost, which will be 10 here. That penalty being incurred from supplying from 2 to node 5 here, which is inevitable if we want a max flow. All right, so this gives us a min cost of our max flow, and again, we can get those values using this syntax here and using those existing solutions in NetworkX for min cost max flow problems. Again, this is a great example of reducing an existing problem into a max flow problem and then using some existing tools, specifically here in NetworkX, to solve that problem, thus solving our original transportation problem. All right, so thank you again for joining me in this video short, and hope to see you in the next episode.